Assalamu alaikum and hello everyone. Today we want to discuss about the steady state error analysis. Let's start. The difference between the output and the reference in the steady state is defined as the steady state error. So the definitions and other details are here. That one you can read by yourself. So now let's consider this negative feedback control system. So you can see our input is RS, is in S domain, and our output is C of S. We have G of S and we have the feedback H of S. E of S is our error. Okay, so now we can write E of S equal from this negative feedback. We can write E of S equal R of S minus, that means E of S equal R of S minus H of S times C of S. Okay, that one you already know. On the other hand, C of S is actually nothing but the G of S times E of S. Okay, so C of S equal G of S times E of S. So now if we replace the value of C of S in this equation, that means here, then what we will get E of S equal R of S minus G of S times E of S times H of S. Okay, then this part you bring it to the left side, then finally we can get it R of S here at the right side. Then you factorize E of S, then we will get this equation, E of S equal R of S divided by 1 plus G of S times H of S. So if there is one theorem here, and if we apply this theorem, then we will get the steady state error, which is, we call it ESS, equal limit S tends to 0 SES. Okay, this is actually from the theorem, and we skip the theorem here. Then is the same thing, E of S equal will be R of S divided by 1 plus G of S times H of S. Okay. By the way, these two formulas are very important because we will be using this formula in this analysis. So it will be better for you if you can remember this both formulas. Okay. The next section is a type of system. The type of system, you can see that if this is an open loop transfer function, that means if we have H of S equals to 0, so what we can do, if H of S equal 1, then what we can get, G of S equal K 1 plus st1 times 1 plus st2 plus dot 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 sn. This is actually is nothing but just an expression. Okay, it's just an expression of G of S in a factorized form. In this case, you can observe that the power of S is n. So now this is the important part. Actually, I skip this part because it's not required. If n equals to 0, so that means if here n is to 0, that means it's become 1. So we call it, this one we call it the type 0 system. If n equal 1, then we call it, this is type 1 system. If n equal 2, this is called it type 2 system. So this all the values, all the different values of n we will be replacing in this equation. Now let's see the example. Find the system type for the given system. This is a system, you can see that. Okay, so the open loop transfer function is the same, G of S and H of S. You know this one because in this case your H of S equal 1. So that means this is the one. This is the one we are applying. And anyway, you can see that this is 1 over, because your G of S is equal 1 over S plus 2. If 1 over S plus 2, in this case, if we try to match this 1 over s plus 2 with this general expression. Remember, this is the general expression, this one. So what will happen? Your 1 is your k, that means constant, and s power of n times 1 plus sta. So s power of n, here you do not have any s power, so that means in this case your s power is 0. So that means your value of n equals to 0. If value of n equals to 0, we call it, this is a type 0 system. Okay, let's see another example. Find the system time of the given system. You see, this is g of s, you say g of s times h of s. So we have, this is the system, and this is again I mean the feedback is 1, so nothing to do here. So we have s cube plus s square plus 2s. That means we can factorize the s. If you factorize the s, then it will become s power of 1. This s power of 1 means that it is a type 1 system. It's as simple as it is. Now we want to go to the next section, which is we call it steady state errors with the various input function. So that means our input will be different types. There are 3 types in this case. One we call it step input, second we call it parabolic input, third we call it RAM input. So we will analyze all of this. So let's start with the step input. You know, this one is step unit means is a u of t, which is like nothing but the 1 when we change it to Laplace transform. So our input is small rt. You know that our from this block diagram, our input is all this input is capital RSP, because it's in S domain. So if it's in time domain, so it will be small rt equal a u of t because of the step unit. A is nothing but the constant. So if we transport this one into the S domain, it will be capital RS equal a over s. If you do not want to write a, is also fine, you can just write 1. So it will be r of s, it will be 1 over s. So now steady state error, that means ESS will be limit. So this is nothing but the formula that we just learned here. This formula, this the formula, or this the formula. So if we apply this formula here, limit s tends to 0, s times 1 over 1 plus gs times hs times a over s. This is not x, this is times a over s. Limit s tends to 0. So you can see that this s and this s is cancelled. So what remains? So a over 1 plus gs hs. Now you see a is your constant, 1 is your constant. So we limit is only applicable for this part, g of s, and h of s. So that's the reason limit we are writing it here. So now let's consider this part, limit s tends to 0, g of s and h of s equal kp. Is nothing but a constant, another constant, which is called the static position error constant. So if this is your kp, so we can write e of ss equal a over 1 plus kp. We can write like this, right? We can write like this. Here, let's say if we want to write like this, ess equal, what we can write, you see that a over 1 plus this part is kp. So let's analyze this kp now for different type of system. So first for a type 0 system, that means value of n equals 0, our kp will be limit s tends to 0 g of s to s. So that means limit s tends to 0. So we, in this case, we will use the general expression, because it's like a theory. If you are given any specific example, so you will write that specific function here. Okay, so k, this is the general expression that we already told you here. This is the one, the general expression. Okay, this is the one, because this it in this case the power of s will be 0, because it's a type 0 system. So that's the reason is there's no s here, become 1. So it is like this. So now you replace the value, because if you take this value of s, the limit value of s is equals to 0, all of this, then it will become 1 over 1. So it means that it will remain only the k. So if it remain only the k, that means kp equals to k. So it will be ess will be a divided by 1 plus k. Okay, done. If it is a type 1 system or higher degree of n, so that means n is greater or equal 1. In this case, kp will be your 1 plus this one and this s power of n, because now your value of n is not 0, it's 1 or more than 1. If the value is 1 or more than 1, so what will happen, this s will remain, and once you replace the limit value of s is in this denominator, then it will become 0. So once 0, so k over 0, it will become infinity. So now you write the steady state error again, ess is equal to a divided by 1 plus infinity, which is 0. Okay, so this is actually for the step input. So next, okay, next we will discuss about the RAM input and also the parabolic input. Remember guys, this RAM input and the parabolic input, RAM input, this one already we have discussed in the in this slide. You can see here, this is the slide number 8, the typical test signal you can see here. So if you see, if you say step input, so function will be u of t, Laplace will be 1 over s. Which is a RAM, if it's a RAM input, then your function will be t ut, and Laplace will be 1 over s square. Okay, you can see that also we are using for steady state error, this also steady state error. If this is a parabolic or parabola, so it will be half of t square divided by ut. Okay, and the Laplace will be 1 over s cube. So this is the